And we're going to go full screen. All right, so hopefully everybody can see the screen. This is Precalculus CP A4, March 26th, 2020. We're getting started today with some area of triangles. How exciting. A brandy new topic. Kind of.
Woo!
Woohoo! That's what I'm talking about. That's what I love to hear. Getting our pre-calc on. So, in any case, little quick do now for you. I'll give you a minute to do that while everybody's getting settled in and everybody's getting situated. Think back to geometry. We're going to be calling back to geometry a little bit today. What is the area of that triangle? Or at least how would you find the area of a triangle like that? I'll give you just about a minute to think about it, ponder it. Just another couple of reminders as you are thinking about that do now. Make sure to take the attendance form on Classroom. Make sure your webcams are off. Make sure that if you have a question, you feel free to ask. Don't feel like you're interrupting. The point is I'm here to help you, so feel free to chime in with whatever you got. But today I'd like to teach you a new way to find the area of triangles. Oh yeah, there's a new way, and we're going to learn that today.
Mr. Giorgio.
Yes, Jacob.
So, one second, sorry. For that do now, in the middle of a triangle going up through the center, is that a 2 or is that an 8?
That is an 8. Sorry if my handwriting's a little sloppy. So we got a height of 8 and a base of 13. So think about it. Hopefully, again, your other classes have been going well so far, which is great. All right, I think we're just about ready to go, yeah? Figuring it out. Okay, fantastic. Let's get it done. So if I have a triangle like that, and again, feel free to either say it or type it in the chat, whatever you're comfortable with. If I have a triangle like that, right, how do I find the area of, this is just a classic geometry problem, how do I find the area of a triangle that looks like that? Does anybody have a thought? Oh, that's right. There's some participation today. You didn't think there'd be participation. There's participation. What do you think? Area of the triangle. Going back to geometry. Any thoughts on how you'd find that? Oh, I love it. Jacob, type it in the chat. 0.5 or 1/2 base times height. Absolutely. That's the classic formula from geometry to find the area of a triangle. We say that the area is 1/2 base times height. Right? Or just filling in that information here, you would say that the area is 1/2 times the base of 13 times the height of 8. And that's going to come out to be 1/2 of 8 is 4. 4 times 13 is 52 square units. Right. Everybody's hopefully comfortable with that. That's a nice little callback to geometry, right? However, it's not always going to be that simple. Unfortunately, in the real world, we don't always know what the height of triangles are, and we don't always know the length of the base. So consider a problem kind of like this instead. Consider now if I had this. Here's my triangle. By the way, just a little FYI, if I'm going to label my triangle as triangle A, B, C, it's common convention to call angles in uppercase letters and sides in lowercase letters. And when you refer to a side with a lowercase letter, it's always opposite of the angle. So for example, this would be side A with a lowercase a because it's opposite of angle A. This would be side B, opposite of angle B. And this would be side C, opposite of angle C. All right. So what if I told you that this side, side A, was 13, this side was 6, and this angle were 50 degrees, and I asked you to now find the area? A much different set of information than was given to you before. If I said that that distance on the bottom is 13, that leg right here, this side right here is 6, and this angle C is 50 degrees, well, what would you do? Well, you might initially be like, well, in order to find the area, don't I need the base and the height? And that's true. I don't have the base and the height right now, but we can find it. We can find it. What you can do is you can drop down what's called an altitude, or just this vertical line that's perpendicular to the base, from angle A, and make a right triangle. Now we have an angle of 50 degrees, we have this side, and we have an unknown value here. So what can we use to link those three things together? We have an angle, we have the opposite, and we have the hypotenuse, notice, across from the right angle. So I can say that this is sine. I can say that to find the height, the sine of 50 degrees should equal h divided by 6, right? Your opposite over your hypotenuse. Solving for that h, I would now see that it's 6 sine of 50 is equal to h. And just using our handy dandy calculator, I actually am somewhat mad because I left my graphing calculator at school. It's still in the building, so I have to use my illegal rectangle right here. But I can do that by saying we got the sine of 50, so I just type 50 times sine, and then multiply that by 6. And I get that, just round up to 4.6, I'd get that my height is 4.6. And now that I know that my height is 4.6, now you can go ahead and just find the area of the triangle, just like we did before. I can say that the area is 1/2 times base of 13 times height of 4.6, and that comes out to be 29.9 square units, approximately. Okay? Hopefully that makes sense how we did that, yes? Just understanding that we can find the height by really turning this into a sine problem. And from that, we can now extract a formula that can be used to find the area of any triangle if we're given two sides and the included angle. By the included angle, I mean the one that's in between it. So, just want to write this formula down for you here, very important. Given two sides and an included angle, the area of the triangle can be found by, it's very similar to 1/2 base times height, but now all we're going to do is instead of this value of h, called the height, we're just going to substitute this, which is essentially this length times the sine of this angle. So your area formula would be 1/2 times the base times this side times the sine of this angle. The way that's usually written is it's usually written as a b sine of c. Because if you notice, put that in a box. If you notice, that's exactly what we did over here. In order to find the area, I did 1/2 of this distance, a, which was the base, times b sine c. Well, that's what gave me what the height was. So this formula of a equals 1/2 ab sine c, that's another way that we can find the area of a triangle using sine. Hopefully that makes sense to everybody. I'll show you another example right now. So suppose that I have this triangle right here. Just looks like that. I'll call this side 7. I'll call that side 4. And I'll say that this angle up here is 73 degrees. And I asked you again to find the area of that triangle. Well, what you could do is exactly what we did before. I have two sides, and I have an included angle, meaning it's in between those two adjacent sides. So I can say my area is 1/2 times ab sine c, which is 1/2 times one of the sides 4 times the other side 7 times sine of the included angle c. Okay. And using a calculator, you would figure out, I only know because I did it off to the side here, just so I wouldn't spend time on the calculator. I know that my area is 13.4 units squared. Okay. Does anyone have a question about how that's done at all? It's just another formula now that we can use to find the area if you're not given the height. If you're given the two sides and two adjacent sides and an included angle. Hopefully we're all clear on that. Okay, good. If you do have a question though, again, feel free to chime in. All right, so what you can actually do with problems like that is mix them up a little bit. Some problems that you see will actually be in reverse, where you'll see something that says the area of triangle PQR is 15 centimeters squared, right? Always a good idea to draw a picture. We'll get to that in a minute. If side P is equal to 5, side Q is equal to 10, we now want to find angle R. So very similar type of problem, but now instead of just given all these characteristics and finding the area, now I just have to find one of those characteristics. Again, a good idea to draw a picture. So we're going to construct a picture just like this. I have labeling P QR. Notice using uppercase letters for the angles. Doesn't really matter where you put those letters as long as they're in order. If this is angle P, then this would be side P. This would be side R. This would be side Q down here. Now just filling in the information, P would be equal to 5, so I know this is 5. This is 10. We don't know what angle R is, but I do know that the area is 15. So I'm just going to use my formula. I'm going to say 15 is equal to 1/2 AB sine C. 5 times 10 times sine of C. And we don't know what sine of C, we don't know what C is, but we can figure that out. We got 1/2, 5 times 10, that's 25. So the 15 is equal to 25 times the sine of C. Divide both sides by 25. You get 15 over 25 reduces to 3/5 is equal to the sine of C. Now in order to actually find what C is, we can take the sine inverse of both sides, right? You remember doing that? Sine inverse and sine inverse, right? Because that would cancel out the sine. And if you use your handy dandy calculator, you'll get that the sine inverse of 3/5 or sine inverse of 0.6 is 36.87 degrees. Does anyone have a question about how that was done at all? It's still using the same formula. It's just now given different information and plugging in different stuff. Everybody's feeling good about that? Confident? Okay. I take your silence as, yes, I feel great. All right. So, again, feel free to speak up if you have anything, though. But really, that is not the entire answer. That's unfortunately only half of the story. This is an answer that exists in quadrant 1 for sure, because if you recall, the sine of any angle is positive in the first quadrant and the second quadrant. So this is the case if this angle were an acute triangle, or that of an acute triangle. However, this would also have a matching quadrant 2 value, a value somewhere in quadrant 2 that shares the same sign as quadrant 1. If you remember, we call those things reference angles, where you could say, oh, well, this angle in quadrant 2 has the same sign as this angle in quadrant 1, right? Because the sign is positive, it represents your vertical distance from the x-axis, and that's exactly what could happen here if you have an obtuse triangle. See this big angle here, obtuse triangle, instead of an acute triangle. Still possible to say, well, this is 5, this is 10, and what's that? You can still make an obtuse triangle with these measurements. So in order to find the matching angle in quadrant 2, it's not really that much work. You just have to do 180 degrees minus your quadrant 1 response. Because remember, that's how you find a reference angle. Going from 180 degrees, which is right over here, and subtracting off our angle will end us in the same vertical position. It'll give us another angle that has that same sine value as this one over here, because sine is positive in the first 2 quadrants. So in short, if you have one of these problems, there's actually 2 potential solutions. One for an acute triangle and one for an obtuse triangle. In order to find them, we just take our acute triangle answer, which is always what's going to come up if you use the calculator, by the way, and then just do 180 minus that to get our other potential answer of 143.13 degrees. That's 180 minus 36.87, and that's our quadrant 2 answer. So there are, given the set of information, there's 2 possibilities for what angle C could be. It could be 36.87 degrees, or it could be 143.13 degrees. Okay? Any questions on that idea? All right. Now, a topic like this is somewhat sneaky, because what ends up happening is, as we go on to the back here, some problems are related to this topic, but they don't seem to be at first glance. It kind of extends to this idea of polygons in general. And if you look at the problem that I'm about to write down on the paper, you might be like, well, how does this have any connection to what we just talked about? This seems like something completely different, but in fact it's not. And I'm going to show you that in just a moment. I can then extend this idea to say, ready? Find the area, don't freak out, don't panic, of a regular hexagon. Oh boy, regular hexagon, good old geometry. Regular again, meaning that all the sides and angles are the same, so it's just a standard hexagon. And hexagon being 6 sides, correct? So it's a 6-sided figure where all the sides and angles are congruent. Inscribed in a circle. Inscribed just means it's contained within. So if it's contained entirely within a circle of radius equal to 4. Okay. If I wanted to find the area of a regular hexagon inscribed in a circle of radius 4, I'm going to try my very best to draw a regular hexagon inscribed in that circle. It's going to be a little difficult. 1, 2, 3, 4. I've got my radius of 4. 1, 2, 3, 4. 1, 2, 3, 4. Oh boy, this is live too, and it's being recorded. No pressure, no pressure. Here we go. Here's my circle coming all the way around. Well, this isn't bad so far. Not bad so far. Okay, now we got the hexagon part. Oh boy. All right, we got a side up here. We're going to have a side here. We're going to have a side here. They're not exactly the same size. Side here and a side here. I mean, that wasn't perfect. That's not terrible, I guess, but hey, you know, we do what we can. But in any case, if the radius is 4, right, then that means the distance from any center to any one of these vertices on your regular hexagon would be 4 units, correct? Because the circle has radius 4. So that would mean that any of those distances would be 4 units. This is 4, 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 and this is 4. Right? We're all happy with that, I hope. Excellent. Okay. And now, if you notice, this problem really, although it says hexagon, circle, it doesn't say anything about triangles, but you can break down this hexagon into just 6 equal, are they equilateral? I don't think they're equilateral. 6 isosceles triangles. But let's just focus on this top triangle right here. We have the 2 sides of this triangle. We can also get its included angle. If the whole way around the circle would be 360 degrees, right, that should be the sum of all these angles added together. This is essentially just cutting it into 6ths. So I could say that each angle of each one of these triangles is 60 degrees. So this would be a 60-degree angle right here. Does anyone have a question as to why that's the case? And if you take a look, by the way, I now have 1, 2, 3, 4, 5, 6 of these triangles. In all of them, I have 2 sides and an included angle. So I can just find the area of one of them and then multiply it by 6. If my picture were 100% accurate, you should see that they are all about the same size. I don't think it's too bad, but hey, you know, we'll keep working on it. So I can say that the area is 1/2. We're going to use my AB sinC formula. 4 times 4 times sine of 60. And there are 6 of those triangles that exist, 6 of these triangles that exist within this hexagon. So we're just going to take that value and we're going to multiply it by 6. Does everybody understand the setup and how that equation originated from that diagram? I hope so. Hope so. So now going from there, it's just a matter of solving. We got the area is 4 times 4 is 16. Half of that is 8. Sine of 60. And then times 6. What's the sine of 60 degrees? Ooh. Ooh. Unit circle. Sine of 60 degrees is? I'm not going to tell you. Now, someone's going to say it. Someone's going to say it. Sine of 60 degrees. I know you know it.
Is it 1/2?
That's the cosine of 60 degrees.
Rad 3/2.
Rad 3/2. You got it. You got it. So you'd say that the area is 8 times rad 3/2. I can play the unit circle video if you want me to. You know where that is on YouTube. You can find it. Anyway, times 6, right? And then you could just say, well, that's the same as 8 divided by 2 is 4, rad 3 times 6, which becomes 24 rad 3 square units. Okay? Or you could approximate that to a decimal if you use your calculator. But that's how it's done. Does that make sense to everybody how that's the case? Good. Once again, I take your silence as, yes, Mr. Giorgio, everything is crystal clear. Excellent, fantastic. We have one more question that I'd like to show you today involving another polygon, specifically a quadrilateral. So how about this one? Remember, a quadrilateral has 4 sides. Diagonals of A. Going for a good old parallelogram. Parallelogram, hope that's spelled it right. Are 20 millimeters and 25 millimeters and intersect at a 50-degree angle. So diagonals of a parallelogram are 20 millimeters and 25 millimeters and intersect at a 50-degree angle. Find the area of the parallelogram. Okay, so let's take a look at what this looks like. A great idea to draw a picture again. Parallelogram starts with 2 parallel lines, just like this. We're going to extend this one a little bit and connect. We're going to extend this one a little bit and connect, just like that, parallelogram. I have my 2 diagonals. Diagonals are just the lines that go from the opposite corners. They connect each other, right? These opposite angles like that. Excellent. Probably makes sense to label my smaller one as 20 millimeters. That's this one right here. And my larger one, this one right here, is 25. That being said, though, does anyone remember, or what do you think the distance of this portion of the diagonal would be? If the whole diagonal is 20 millimeters, do you remember what this and this would be? Independently? Any idea? Anyone remember from geometry, going all the way back? The whole thing is 20. The diagonals cut it. Oh, we got Jacob in chat. 10. Absolutely. Yeah. If you recall from geometry, or maybe you don't remember, maybe you'll remember now, the diagonals do bisect each other, meaning that they split each other into 2 congruent pieces. That may have been a tough one to recall from geometry, but it kind of makes sense. Even just looking at the picture, it kind of looks like, oh, they're about the same distance, and that's exactly true. If that diagonal is 20, then this one is 10, and that one is 10. If this diagonal is 25, then each one of these is 12.5 and 12.5. Now, we really just have, yes, we do have a parallelogram, but don't we really also have 4 triangles here? If they intersect at a 50-degree angle, it probably makes sense to call this the 50-degree angle, right? Because it looks like the acute one. If that one's 50 degrees, well, that one plus this one should make your 180 degrees, because that would create a straight line right here. If that's 50 degrees, this one has to be 130 degrees. This one is vertical of this, so also 50 degrees. And this one's also 130 degrees, because that completes your entire 360 degrees. And now, if you take a look at what we got going on here, notice I have 4 triangles, all of which have 2 sides and the included angle. 2 sides, included angle, 2 sides, included angle, 2 sides, included angle. So we can use our sine formula that we just came up with to figure out the area of each of them. I have 2 of these and 2 of these, so we're just going to go ahead and do them separately. I can say, well, the area is, let's do these acute ones first. To do the acute ones, we're going to say we got 1/2 times 10 times 12.5. Those are my 2 sides, times the sine of 50. And we have 2 of them, so I'm going to multiply that by 2. And we're going to add that to the others, right? Because that's going to make up all 4 triangles. We got 1/2 times 10 times 12.5, just like before, times the sine of 130 times 2. And again, times 2, because there are 2 of those triangles composing our whole shape. So, plugging into a calculator really quickly, I'll show you here, just so you see how it's done. Plugging into a calculator, I got 1/2, so 0.5, times 10. I'll do the top ones first, times 12.5. Oh, whoops. 12.5 gives us 62.5. I'm going to multiply that now by the sine of 50. And I get 47.87. Let's round that up to, oh, sorry, times 2, right? Because now we're going to double it. Sorry, that's 47.87. I'm now going to double it. And we got 95.75 I think we can round that up to 95.8. So we got the first one is the area is 95.8. How about the second one? Ready? We're going to do 0.5 times 10 times 12.5. This is now for the obtuse triangles. Times the sine of 130. So 130 sine of that. I get 47.87. This is looking awfully familiar. This is looking awfully familiar if you ask me. So that's now times 2 is also 95.8. How crazy is that? How interesting. This calculation came out to be the same as that calculation. Why? Why do you think that's the case? I'm going to ask you. In the meantime, while you think about that, why do you think this area is the same as this area? How are these two values connected to each other? Think about it for a minute. In the meantime, we just add these together. We can get that the area is, let's see, 95.8 times 2, which is 191.6 millimeters squared. Does anybody have a thought, though, as to why this calculation would come out to be the same as this calculation? Why is that the case? So all 4 of these areas are the same, which is true, by the way. But why? Why?
Would it be that one triangle's in quadrant 1 and the other's in quadrant 2?
Paige, you are on the ball. Absolutely 100%. Yeah, this one right here, 50 degrees and 130 degrees, those angles have the same sine value. This one would exist in quadrant 1 if it has that 50-degree angle, and this one would exist in quadrant 2. It's exactly what we just talked about before. That was a little crooked, but if I have my sine of theta, we know it's positive in the first and second quadrant. 50 degrees would exist just beyond the 45-degree mark, and 130 degrees would match it on the other side. These would have your same vertical distance from the x-axis, again, if I'm more of an artist, and you would see that these are exactly the same. And so therefore 50 degrees and 130 degrees have the same sine values. That's why all 4 of these triangles have the same area, but this is a breakdown of specifically how you get it. It's the exact connection that we brought up over here, whereas both of these triangles exist, one in the first quadrant, one in the second quadrant. All right? So hopefully that makes sense. The point of these back 2 problems was really just to show you that problems involving polygons really can just be broken down into triangles. And when you break them down into triangles, you can use all of our trigonometry stuff that we've talked about, using the 2 sides and the included angle in order to find the area. Same thing over here. 2 sides and the included angle, 2 sides and the included angle. Just be mindful of the fact that when you're going in reverse, you do end up with 2 possibilities for your included angle, because you could have an acute triangle or you could have a larger obtuse triangle. All right? But that's pretty much all we got for today. It took us right to the end, which is fantastic. I want to remind you that there is an assignment posted on Google Classroom. It's a couple practice problems on this idea. I'll be happy to go over them at next class if you so desire. Additionally, we're going to be going ahead and learning something called the law of cosines and the law of sines, both of which help with this idea of finding the area of triangles if you're given all different pieces of information, right? It's not always going to be base times height. Here we see 2 sides and an included angle. What if you're given a separate piece of information? How would you find the area? That's what's coming soon. All right. If you do have any questions, though, feel free to ask. This lesson will be available to watch after the fact, so you can go ahead and check that out if you missed it. But other than that, that's all I got for you today. I hope you have a fantastic rest of your day and a great weekend, because I won't even see you tomorrow. So I hope you enjoy your weekend. I will see you on Monday. Again, please try to get those problems done. And thank you for your attention and cooperation today. Have a great day.